right, continuing on with our study. So far, all of the functions that we've worked with have been non-negative, which means positive or at the very minimum 0. So that makes it really interesting when you're doing an area under a curve, okay, say of something, you know, like this. Well, it's easy because it's all positive, okay? But what happens if your function goes below? All right, things change a little bit. So if f of x is non-negative, then the area under the curve every single time can just be defined as the integral from a to b. All right, however, if f of x is negative, like in this example, okay, over a certain interval, then the area from a to b is the opposite. Okay, because if you type something like this into your calculator, you're going to get a negative number. All right, so the area, the actual area, is going to have to be the opposite of that integral. All right, and that is because area is always positive. Okay, so in general, this integral does not give us the area, but rather we would call it a net accumulation. It kind of adds up the area and subtracts the areas below the curves. All right, so for example, if you have a function from a to b or certain numbers, and you want to integrate it, okay, like on this example, if you just do integration from -5 to 5 of f of x dx, you won't get the total area, okay? It's not equal to the area. And that's because this function here, it starts out, it's positive, negative, and then positive. So whenever we're integrating from left to right, just like we read, okay, anything above the x-axis is positive and below the x-axis is negative, all right? So, you know, if we're thinking about something here, say you start, I don't know, cupcakes or something, right? So here you're starting with a positive number of cupcakes, and then you eat a couple, so you lost some. So you're going down, the net accumulation is going down. But it looks like this area, the positive area, is more than the negative area. So maybe you have a few left. And then your friend felt bad because you only had like 2 cupcakes left, so they made you some more. Okay? That's from left to right. Anything above the x-axis is positive. Anything below the x-axis is negative. All right? When we're doing these integrals. Now, if we go backwards, okay, if you integrate from right to left, so if we go from -2 to 5, okay, or from 3 to -2, that's backwards. That's the opposite of what we would think about doing, okay? So in that case, it's the opposite of what you would think. The negatives are going to be above the x-axis, okay? And the positives will be below the axis when you're integrating from right to left. And we'll do a couple examples. It might help to clear that up a little bit. All right. So in general, if you integrate from right to left, it's going to be equal to the opposite of integrating from left. I went backwards. Okay, from left to right, it's going to be the opposite of integrating, okay, the other way, from the right to the left. All right, let's just look at an example. Blah, blah, blah. All right, very important. Area is always positive. Area is always positive. Every single time. Area is positive. You can't have a negative area. All right, and integrals are not always equal to the area, as we saw on the last page. But we can use integrals to help us find it. We have this graph, y equals f of x, shown below. The area of the region here, okay, the area of this region is A1. The area of this region is A2. Okay, they're positive numbers because they're areas. So we're going to try to find different integrals. So from here, we want the integral from -4 to -1. So that's going from left to right. So that's our normal case. All right, so if we want to integrate that, that's just simply going to be equal to A1. All right, that's our normal. The area actually matches the integration this time. All right, let's see what the next one, -1 to 4. because this is going from left to right, okay, and it's below the x-axis, this is going to be negative a sub 2. All right, now this problem, we're going backwards. We're going from 4 to negative 1. So we want to think backwards of what we would normally do, okay? So this case, since we're going backwards, normally that a sub 2 should be negative. Now it is positive. All right, negative 4 to 4. Now we're taking into account this whole region, and we're going in our normal left to right fashion. Okay, so we're going to have a sub 1. We're accumulating that. And then we have to subtract a sub 2 because it's below the x-axis. All right, and then part E is combination of a few things. And this actually came from one of the released multiple choice questions. Okay, and this one's just kind of broken down, but the multiple choice question was to simplify this. All right, and a lot of people make mistakes with signs and everything. So let's just break this down. We know this part. We're going from left to right, and we know that's A1 minus A2, and it's minus A2 because it's below the x-axis. Okay, it's the area of the first one minus the area of the second one. Okay, minus 2 times. Now, what's the integral from negative 1 to 4? And we already did that. That'd be negative a sub 2. All right, so rewriting this, a1 minus a2 plus 2a2. It ends up, in this case, a1 plus a2. All right, so for this integration, that would be the numbers that represent that integral. All right. In general, if you want to integrate, let's say from 1 to 5, you could rewrite it as the integral from 1 to 2 plus the integral from 2 to 5. And you wonder why you would have to break it apart to make it worse. Well, you'll see that pretty soon. You can also go from 1 to 20 and then 20 to 5, right? You could go from 1 to 200 and 200 to 5. It doesn't matter what C value you pick, but this is a property of integrals that we can now use. Okay, so we're going to approximate this integral using 4 subintervals of equal length using the midpoint, Riemann sums, and trapezoidal methods. Okay, test our answers against the calculator's approximation. So here we go. Maybe it'd be helpful to get a little sketch of this picture. And it's x squared minus 4. So it's going to look something like this. And I'm not going to be able to really approximate the picture very well. Where this is 5, it's going to be crossing at 2. So that's 3, 4, and 1 is right here. So it uses 4 subintervals. So the delta x, we're going to approximate it. Remember, it's b minus a over n. So delta x, we're going from 5 minus 1 over 4 subintervals. So that's going to be 1. So not too bad. All right, now we're using a midpoint approximation first. And we're doing this area and this area. Okay. All right, so midpoint Riemann sums. We're going to take the midpoint value. All right. And my picture is not necessarily drawn to scale here. And the midpoint might be about that. So okay, so the midpoint, we could say that the integral, this is the important part, you're approximating it by doing a midpoint Riemann sum. All right, so our rectangles are 1. They're all with a 1. 1 times. Always show. Okay, don't just throw the numbers in there. Show what you're doing. Whenever you want to do a free response or open-ended kind of problem, you want to show the reader or the scorer what you're thinking about doing. Okay, that way you can get points just for putting basic things down, all right, even if you can't crunch the numbers or do anything else. So this would give you a point or two just for setting it up and showing your work, even if you can't do anything else. So for our midpoint Riemann sums, I just used the midpoint, 3 halves, 5 halves, 7 halves, and 9 halves. Okay, now I'm going to actually plug in the numbers. So I don't feel like thinking too much. Let's do it this way. 9 fourths minus 4 plus 25 fourths minus 4 plus 49 fourths minus 4, and I'm just plugging them into my function. Okay, plus 81 fourths minus 4. All right, and that would be the same as I believe, if I can add right, 164 fourths minus 16, which would be the same as 164 fourths minus 64 fourths, or 100 over 4, or 25. All right, now, and again, on a free response question, you could just leave your answer right there. You don't have to do any more. But because we're looking at different numbers, I like to get numbers to see what's happening. All right, but on the free response, you can stop right once you get the numeric parts. This part, you cannot stop there. Okay, don't do that. But you can stop right at that part. All right, so we'll just continue a little bit more. We're going to do our trapezoids. So we're going to approximate this integral, approximated by the trapezoidal, this time approximation of area. So now this case, we're going to use trapezoids. And this trapezoid is actually a triangle, but that's okay. Let's see, here to here, here to here, and here to here. So it's going to look a little bit closer to the area, this number. So we're going to show what we're doing. 1/2 times 1, and this is going to be f. Am I doing this right? Yep, f of 1, okay, plus 2 times f of 2, plus 2 times f of 3, plus 2 times f of, what am I doing this? 1, 2, 3, 4, 4, plus f of 5. All right, now I could just plug in those numbers. 1/2 times, what do you get? -3 plus 2 times 0 plus, I'm just going to write that. 2 times 0 plus 2 times 5 plus 2 times 12 plus 21. All right, 1/2 times, I think adding that up will give you 52 equals 26, which is close to our other one. Okay, I'd like to see if I'm even setting this up right. And again, you could stop right here, but to kind of move forward, I wanted to do that. So now, can any of these approximations represent the approximate area of the region? No. No, it cannot, because this part would be negative, okay, and this part would be positive. We can't use this integral to represent the area. And test your answer on the calculator, okay, and again, to type that in, you're typing in the integral symbol of your function, x squared minus 4, comma, x, comma, and where you're going from 1 to 5, close your parenthesis, okay, and you should get a number, and I think we get about 25.333, so it was a pretty good approximation. All right, so one last thing, example 6 here asks you to approximate the area of the region in the previous problem. All right, so I gave you all the tools. Only one thing changes, only the sign of this part changes. So I'd like you to go ahead and approximate the area of the region in the previous problem. All right, so in your whisk, I want you to write area. You could say midpoint 4 equals, and you should put approximation, but if you can't do that on the calculator, that's fine. And then give me an answer, and also the area that's approximated by the trapezoidal method. Okay, and again, it's very similar to the setup, only this time this part is negative. Okay, that area is negative. This area, well, the area isn't negative. Sorry, let me correct myself with that. This area, okay, is below the x-axis. So when we do an integral, it's considered negative, okay? And this part is positive. So again, I'd like you to finish up with that.